SHE-SOTis, and sorry for those who came to listen to to Matthias and end up stuck with me. So it's a good opportunity to be here anyway. And thanks to Chan for giving me this opportunity. So today I'm going to talk about current-driven doing wall dynamics in ferrimagnetic manganese nitride, and this is a collaboration between our group in Institut Néel in Grenoble, Spin-Tech laboratory, and then the samples that I'm going to present were made in Tsukuba University in Japan. I was going to present you, where we come from. So since we are at the seaside, I'm going to show you some mountains. So we are in Grenoble, we are surrounded by mountains, and we are on this Polygon Scientifique, so we are close to European synchronous radiation, neutron facility, and we are at the CNRS Institut Néel, and we are close to our people from Spin-Tech that you might know better than Institut Néel. So this is to go down, sorry. Manganese nitride is one of the few known magnetic nitrides that are presented here. They are all grow in the antiperovskite structure, and we thought it could be interesting for spintronic applications because they are made of cheap, light, and abundant elements. They don't have any critical elements like cobalt, heavy metals, or rare earths. So in the bulk, manganese nitride grows, so it's a ferrimagnetic material with the two sublattices corresponding to what is called manganese 1 in the corner side, and with this large moment, and manganese 2 in the face-centered moment. The easy magnetic axis is in the 1-1-1 direction. It has pretty high Néel temperature, and in the bulk is a non-collinear ferrimagnet. But we are interested in thin films. These thin films, as I said, they are made by our colleagues in Tsukuba University in Japan. They are made on, we studied once depositing strontium titanide, STO. Their typical thickness is of the order of 10 nanometers, and then they are covered with silicon oxide to prevent further oxidation. So these samples are made by molecular beam epitaxy. They have, because of the very small mismatch between the two crystal lattices, they are very nice. They have a very nice crystallographic structure, as seen here by TM measurements. So very good epitaxy with a very sharp interface and practically no dislocation. What about the magnetism? Yes, from the magnetic point of view, we find that the tensile stress gives rise to perpendicular anisotropy. So we have this 100 texture and also magnetic anisotropy. So what I forgot to say is that the magnetization is the net magnetization is parallel to the manganese 1, so perpendicular here. VSM squid measurement shows also out-of-phase magnetization with a very small, so it's a ferrimagnet with a very small magnetization. Just to give you an idea, 70 kiloohm per meter corresponds to more or less 15 times less than the magnetization of 1 nanometer of cobalt in the systems that we are used to. Large PMA, and just to make sure, so there is no magnetic compensation temperature because the evolution of the two manganese sites is the same in temperature. And then we were surprised the first time that we put these thin films in our Kerr microscope, and we saw these huge domains, so they're like 1 millimeter size domains, which reveal that they are due to the good crystallinity, so the very small density of intrinsic defects. So as I say, it's a ferrimagnet, but no compensation. So what we asked our colleagues in Japan as if they could dope the samples with nickel or whatever and try to obtain this compensation. And this was done by doping with nickel. So they doped the samples with different concentration of nickel. So for me, X is the concentration in the formula units, so between 0 and 0.20. They managed to conserve a very nice epitaxial growth, 001 orientation, and then these CDX measurements show that the nickel had a very nice distribution, a homogeneous distribution within the layer. Yes, so there are neutral, okay, via XMCD measurements, they found out that the nickel was actually substituting the manganese 1, so this corner side, and their magnetic motion was anti-parallel to the one of the manganese, so which means that by increasing the concentration of nickel, you can reduce the magnetization, and then it was expected based on what is known about what they measure about the neutron scattering measurements on bulk system. They found that they expected to have compensation for about, let's say, 20% of 20x6, so 0.18 in a formal unit. This was confirmed by the measurements of our colleagues in SpinTech. By anomalous Hall effect, they showed that by increasing the concentration of nickel, they had a change of the sign of the anomalous Hall effect angle, which indicated that about 20% as predicted by the theory. Our VSM squid measurements also show that it should be around this concentration by 20%, where the compensation, concentration compensation was expected. Okay, so what about, the main talk is about the current-driven domain wall dynamics. So for this, our samples were patterned into strips. So these are 2 micron and 1 micron strips. These are Kerr measures, so differential Kerr images. So the contrast here that you see corresponds to the displacement of the domain wall driven by current pulse. And you can see here both this contrast, so this length stays the same. So there are very small dispersion of the displacement of domain walls with the current. Also related to the fact that we have a crystalline system in which we have a very small pinning of domain walls. So of course we change the current density, and this is the velocity, the domain wall velocity versus current density. So you can see, so we see this large, for those are, notice, okay, so we see this very large velocities of the order of 1,000 meters per second for 1 to the 12 amperes per square meter, and for those who are in that field, these measurements, these velocities are more or less of the same order of magnitude of the ones that are obtained by spin-orbittorque in system with Dzyaloshinskii-Moriya interaction. But what was peculiar here and surprising is that the domain walls move parallel to the electron flow. So the question is, what is the mechanism that responsible for domain wall speed? Sorry. So as you may know, there are 2 phenomena that can be invoked. The classical spin-transfertorque that was studied a long time ago. Actually, it was mainly studied in the years 2000-2010, at the beginning of, let's say, when we started working on this system. So a long time ago, mainly on permalloy. At that time, so the domain wall velocities, the maximum velocity was about 100 meters per second. The domain walls move parallel to electron flow. I didn't say anything about the phenomenon. The current is spin polarized within the ferromagnet because of conservation of angular momentum. When the electron spins aligns parallel to the magnetization within the domain wall, a torque is exerted on the domain wall that moves the domain wall in the direction of the electron flow. So what, at the moment, let's say that recently there have been practically no measurements on samples in which the spin-transfertorque was supposed to be the phenomenon that drive on domain walls, especially since up to now there are practically no effect in systems with perpendicular magnetic anisotropy. And why? So in the year 2000, people were concentrating on platinum cobalt multilayers in which there was no inversion of symmetry. And what was found out, for example, in platinum cobalt multilayers is that there was insufficient spin polarization to move domain walls. But as you probably all know, in the last 10 years or so, we have concentrated on samples in which cobalt or ferromagnetic layers are deposited on heavy metals, and so we have a spin orbittorque that moves domain walls that are stabilized, that have a certain chirality stabilized by Dzyaloshinskii-Moriya interaction. And Matthias has just talked about that. And in that case, what has been found is that the larger velocities are obtained in systems with, ferrimagnetic systems close to the angular compensation. And in that case, domain walls can move either in the direction of the electron flow or in the direction of the current, because this direction depends on the size of two interactions. It depends on the sign of the DMI, so the chirality of domain walls, and on the sign of the spinal angle, so depending on platinum or tungsten on the heavy metal. So in our case, domain walls move, is it this one? Yes, no. Moves in direction of electron flow. So so we were convinced that it was the spin-transfertorque is the phenomenon that drives the domain walls. But to completely exclude the presence of spin-orbittorque, we also measured DMI in this system. So we did domain wall speed measurements driven by an out-of-plane field in the presence of an in-plane magnetic field. And we saw that the domain walls moved symmetrically in the presence of the magnetic field. And this completely excluded the presence of DMI, although we didn't necessarily expect DMI in this system because of the absence of heavy metal. So we concluded that domain walls are blocked in this system. So as I say, there is no spinal effect material. So we expect the domain walls to move in the direction of the electron flow. So the conclusion was the domain walls are driven by spin-transfertorque, and this is the first demonstration of efficient spin-transfertorque in a system with perpendicular magnetic anisotropy. If you take the 1D model for spin-transfertorque driven domain wall motion, you see that so the efficiency is essentially driven by is given by the ratio between spin polarization and magnetization. So we have a system with a small magnetization because it's a ferrimagnet. And then by fitting this curve, we found out that the polarization was about 65%, so which explains why we have this large this large domain wall movement. But as I say, but when we dope these samples with nickel, then we can decrease further the magnetization and go towards the compensation. So let's see what happens when we increase the nickel doping. So this is the first sample in which, so the sample without doping, and this is again velocity versus versus current density. So now we start doping the sample, and I present here the velocity for this current density as a function of magnetization. So we go closer to the magnetic compensation. We keep doping the sample, and then so increasing the nickel compensation. And then once we cross the magnetic compensation, then we have a change of the direction of motion of the domain walls. And then, okay, we go further, and then we decrease again. So what are the main results of this study? The first one is that we have this huge domain wall velocity. So we get to 3 kilometers per second, so 300 meters per second close for this this corresponds to about I think 18%, 0.18 of nickel doping, and then also, so this is the first result, and the second is that the reversal of domain wall motion when we cross the magnetic compensation. To be noticed that if we take, for example, a system with platinum, gadolinium, cobalt, and it's driven by spin-orbittorque, the domain wall direction does not change direction when we cross the compensation, because, as I say, it's the DMI sign and the spinal effect sign that is not expected to change across the compensation. So it is really typical of this system. And then, okay, so we were happy to see these large velocities that are actually comparable or even larger than the fastest measure with Néel was in ferromagnets driven by spinor torque. so if we wanted to, in order to explain these results, we considered the QFE model that was adapted to a ferromagnet close to angular compensation. So in general, with these parameters, so this model was developed in the case of a ferrimagnet, so an intermetallic, so gadolinium cobalt rare earth transition metal effects, in which the germinating ratio for the transition metal and the gadolinium are different, so you need to consider, so you will have that the angular compensation point and the magnetic compensation will not the same, will be distinguished. So in our case, we consider the fact that the two magnetic sublattices are composed of the same metal. Therefore, we made the supposition that gamma 1 and gamma 2, so we suppose that the ferrimagnetic ratios are the same for the two sublattices. In this case, it means that the magnetic compensation and angular compensation point will be the same. So the velocity is given by this expression, and then you expect that the magnetization would, the domain wall velocity would be vanishing close to the angular compensation point. So we fitted this data with this, our data with this formula, and then, and this is the best fit that we could obtain. And there are three parameters: the spin polarization, the damping, and then beta, that is the adiabatic term for a spin-transfertorque. And then you can see that we have this very small contribution of the magnetic torque and this large magnetization. So, this large polarization. So our conclusion was that the large spin-transfertorque domain wall velocity can be related to the increase of the domain wall velocity close to the angular compensation and to the large spin polarization that is given here. And last thing to say is that according to the model, you have a vanishing magnetization, vanishing velocity at the angular compensation point. This point where in our fit the velocity is cancelling is the magnetic compensation. So this confirms the fact that our supposition, the gamma 1 and gamma 2, so not considering two different ferromagnetic ratio was right. So I think I finished. How long do you have? Am I long? Okay, then it's fine. Okay, so the last discussion was about what about the change of domain wall direction. So in the model that was that I just discussed, the sign of the change of the domain wall direction is due to the fact that across the compensation you will have a different, the reversal of, it's due to the change of the relative direction between the angular momentum and the spin polarization. And this was the case in, if you take platinum, gadolinium, cobalt, the spin polarization belongs to the, how do you say, would be the cobalt that, the ferromagnet that would be responsible for the spin polarization, and then the direction of the motion will change across the compensation where the magnetization changes sign. So in order to explain this, we'll have to prove that the spin polarization does not change direction across the angular compensation, and for this we asked our colleagues from SpinTech to carry out band structural calculations, and what they showed is so they considered two systems, manganese nitride and manganese, so undoped and doped sample across the on the other side of the compensation. And what they found is, so these are the density of states at the Fermi level for manganese 1 and manganese 2. What they found out is that the majority carriers in the manganese 2 sublattice was carrying the spin polarization both above and below the compensation. So this proves that the spin polarization doesn't change sign as the nickel composition is increasing, increased, and this can explain our result. So the fact that the relative orientation of polarization and magnetization across the compensation explains the variation of the velocity, the domain wall velocity direction while crossing the compensation. So I think it's finished. Yeah, I just wanted to situate our results in the, let's say, in the state-of-the-art results on the field. Up to now, so these are the results of the spin-transfertorque from, let's say, the year 2010. We have the spin-orbittorque driven domain wall speeds here with the maximum on the platinum gadolinium cobalt from the beach work, from the beach group. So they had a bit more than 1,000 meters per second close to the compensation temperature in this system. Then we have all these results here are taken for, so they are garnets, so you can see these huge velocities for the magnetic garnets, but in this case, the magnetization, actually the domain wall, so these are spin-orbittorque driven domain wall speeds, but in this system the DMI is not strong enough to have Néel walls, and so an in-plane field was applied in order to move the domain walls. So these are all in-plane magnetic field applied on top of the current. So let's say that our final message would be that spin-transfertorque, although it seems to be an old subject, we can show that it's still interesting if you find a sample that have a low magnetization and a high spin polarization. Yes, and this is my conclusion. Thank you very much.
Okay, so thank you, Stefania, for sharing these wonderful results. Okay, questions? Yes, please. Microphone.
Yeah. Can we say that magnetic properties here in these materials are mainly determined by the large PMA? And the second question, did anybody try to do ferromagnetic resonance experiments on this material?
The second question, I don't know. I don't know, because we are not doing that. But the first one is no, it's not a perpendicular magnetization. So the fact that perpendicular magnetization is there, of course, is interesting because domain walls are narrow and then you can move them fast. But no, the most important property is the fact that it's a ferrimagnet and with a low magnetization, and then especially across the compensation, then we have, I mean, everything is just due to the fact that spin-transfertorque is proportional to P, spin polarization, divided by Ms. So it's really one, the large spin polarization, and two, the small magnetization. Then it's perpendicular, so it's another.
And what about ferromagnetic resonance?
I don't know. Sorry, we are not doing it, and our colleagues in SpinTech don't do it, and I'm not sure that. I think it has been tried by our colleagues in Japan, but I don't know. Yeah, I'm sorry.
But it's a natural thing to do.
Yeah, I know. Yes, but I think it was tried for try to obtain the alpha. In fact, I think it was done because they found that, yes. In fact,
as soon as you finish static.
Yes. They did it, and I think that they did it because we also needed the damping factor, and in fact, it turns out that they found the damping factor was 0.017, I think, and it corresponded to what we found from the fit of our data. Yeah. Yes.
Yeah, thank you for the talk. I'm not that familiar with this type of spin-transfertorque driven domain wall motion, but if I remember correctly, you need Bloch type domain walls, and also you have a problem that the Walker breakdown limits at which velocity you can drive.
But that is the case for magnetic field driven domain walls. That is okay. The Walker breakdown is actually yes, but okay, because there are two regimes. Okay, here we are in a regime that is beyond the Walker breakdown. In fact, Yes, because the breakdown in the systems is very, very low, because the Walker breakdown corresponds to the field in which you go up, you start, this is a precession regime. We are already beyond the Walker breakdown. The Walker breakdown is determined by where you start, you kill the demagnetizing energy of the domain walls, which is extremely small in the sample because the MS is practically zero. So this is beyond the Walker breakdown.
Okay. Okay. Thank you.
Yeah. Everything is in our first paper, Nanoletters 2020.
Okay, here.
Okay, thank you for the nice talk. My question is about the fitting. You use the Q5 model to fit the velocity against MS.
The second,
In
the second one or the first one? I mean, with nickel or without nickel?
With nickel. When you change the saturation magnetization here,
Yes.
and you have three parameters here, you
Yes.
said. My question is whether these three parameters also fit the velocity against current linear response in the precessional regime, because it's the same parameters that enters the law,
Yes.
the mobility. I mean,
So
it's,
you want to know if it's fitting?
I guess it's
this
a
one?
nice,
Yeah. Of
yeah.
course. Yes,
But
yes,
it's
yes.
but you only fit these parameters in the other curve, and then you check that it works
Yes.
here.
No, but then it was done individually for each. Yes, of course.
Great.
Yeah, yes, yes. I mean, that was taken just for one domain, for 1 to the 12. Yes, but it was fitting. Yes.
Any other question? Yes, Sabri.
So thank you very much for the nice presentation. I wanted to ask a question about the second fit. For
okay, the one
the
with-
spin torque coefficients, spin transfer torque coefficient for the polarization and non-adiposity. Yeah. So when I want to do micromagnetic simulations, these are basically my inputs. But since you have the domain wall velocities for different systems, basically, because
yes,
they
there
have
are
different
samples.
dopings,
Yes.
I would somehow expect that this parameter should also then change for the system, so that they're not constant for the entire model, but to be depend on the doping ratio.
Yes,
What
but
do
you need to know that the doping ratio is extremely small. So
Okay.
even the maximum, the 20% corresponds
Yeah.
to 4% of doping.
Okay. I see.
So it's really nothing. So okay, you are right, but the concentration is very small. So, but
Okay,
also you
I
can
see.
see that you can say that the fit is not perfect, but okay, the magnetic parameters really change very little.
Mhm.
Yeah.
Okay.
Yeah.
Thank you.
But it's a good question, yeah, of course. Yes.
Okay, let's thank Stefania again and move on.